Welcome everyone, and thanks for joining us today for our SBOM webinar. I'm Maya Portnoy. I'm a product manager here in Incredibuild, and with me we have Tal Kaptan, director of R&D in Incredibuild.
Hi, everyone. Glad you're here. I think it's obvious, but today we're talking about SBOMs. And I want to be upfront. This isn't going to be a theoretical talk about what an SBOM is or why you should care more about compliance. We're going to share with you something that surprised us, something we found while actually building an SBOM product. By the end of the session, we think that you look at your own SBOM very differently. Let's start with the story. A few months ago, I was working on a small project and needed a JSON library. Like everyone these days, I asked my Cloud Code which library to use. It suggested one that looked reasonable to me. I added it to my code base and pushed a PR. A few minutes later, I got an alert from one of our scanners, a known CVE in one of my dependencies. I got back to my code, I tried to search for that dependency, and nothing. I couldn't find any evidence. Clearly a false positive. Out of curiosity, I asked my Cloud Code again to recommend me an open source tool that can scan my project and list my dependencies. I ran it, I got a completely different result. I mean, same code, same projects, but two different answers. This made me think, how can I know which output I can actually rely on? And why those different tools are giving me different answers? That's exactly what we are here to talk about today. Not do you have an SBOM, but is your SBOM actually telling you the truth?
Thank you, Tal. So let's have a quick look through today's agenda. First, we're going to start with why SBOM is especially relevant today. What's changed in a few years that the market is much more urgent today. Then we're going to talk about the accuracy challenge, and also especially in CNCPP environment. This is a real core problem that we're going to address. After that, we're going to cover the illusion of control. Why we believe that existing approach creates the feeling that you have visibility, while in reality you maybe not have the full picture. From then, we'll introduce you the build time approach, our new approach for generating an SBOM, and we will share with you how you can measure your own SBOM accuracy from real methods that we learn. And finally, we're going to wrap up with a demo and a Q&A session. Feel free to ask anything, and we're going to try to answer everything that you wanted. So we have a lot to talk about it, and let's start. So I want to open this webinar by addressing why SBOM has become such a hot topic these days. I'm sure everyone here already have some sort of answer. I mean, you did sign up for an SBOM webinar, but I do want to focus on two core reasons. The first one is regulation. Although SBOM, it's not a new concept in the software security world or supply chain security world, it is a new concept in the regulation world. And we actually see it started only last year. And we see the regulation started with the FDA requirement for medical devices only in February 2025, and then to the US Army Defense. And only last month, in February 2026, we have a huge regulation, NIST regulation, which means that every software company that wants to sell to a US federal government gonna be obligated to have those SBOMs. And if we look a little bit into the future, we also see that in September 2026, Europe regulation also kick in with the Cyber Resistance Act. And this is a huge regulation. It declared that every software company that wants to sell software in Europe gonna be obligated to have an SBOM to their solution. So we can definitely feel the regulation kick in. So this is the one reason. And the second reason, which I know you can probably guess, is of course AI.
Yeah. AI generated code. I mean, it's everywhere. Today we use AI agents to write code and even generate content to this presentation. But there's a side effect. You have more code in production, faster, but also much more unknown. That tension is what makes SBOM accuracy so urgent right now? So Maya, why is it so hard to get it right?
It's a very good question, Tal. Let's dive into it. When we researched this topic, we discovered four main reasons why achieving SBOM accuracy is so hard. The first one is that a lot of the time, what was declared in our code does not equal what was actually shipped. Let's say, for example, I'm a developer and I'm using some sort of security library, but I didn't pin the specific version. On my developer laptop, one version got picked, but on the CI server, when I push the code, totally different one got picked, maybe with a known vulnerability. We don't know which version actually got linked and shipped to our customers. So this is a huge problem, the first one. The second problem, we call it the hidden transcendent dependency. It means, again, that I'm a developer and I'm declaring usage of 10 dependency in my code. But what I don't know is for those dependency to work, they need other dependency. And maybe those other dependency also need other dependency. And then like we have a full dependency tree that me as a developer is completely blind for me. I declare only the first top 10, but actually in my code that I send to the customers have like 50 dependencies. So this is our second main reason. The third one is environment dependent builds. What does it mean? It means that from the same source code, if we use it in different machine, different operation system, we have some dependency for Linux, some dependency for Windows. Maybe we have compiler settings or configuration flags, so many things that from one source code, you get totally different set of dependencies in the final executable. Like this is huge. And the fourth reason that we found out is we call it runtime loaded component. Those are some libraries that never appeared in the beginning in my manifest. They're not declared anywhere, but they get pulled into dynamically at runtime based on the platform I'm using, based on the build system. So they are there, but we didn't know they are there. So keep those four in mind, and we're gonna address them a lot today. And I thought when we started this subject that this is hard, and some languages, this is the four main reason. But then we dive into C++. Tal, help me.
Yeah, okay. C++. Well, it's like the final boss in the game. C++ is in the category of its own when it comes to SBOM accuracy. If you look at the survey data, it's from 2025. It's not a tooling problem. It's a structural reality of the ecosystem. Every modern language has one standard to declare dependencies. I mean, Python has pip, Rust has cargo, JavaScript has npm. It's one file, one lock, but C++ has none of that. In C++, dependencies may be spread across CMake files, scripts, folders, or not declared at all. A developer can vendor a library directly into the repo, add it as a Git submodule, or even worse, download it during the build, or simply copy it into a third-party folder. And when you know what's coming in, the build system itself can change what actually ships, whether it's Windows or Linux. C++ projects often use CMake, msbuild, make, ninja, plus custom scripts and post-build steps that may add, remove, or modify files after compilation. So scanning the source code files alone can miss what's actually in the artifact and what gets delivered. Then there's also static linking. I mean, with dynamic linking, your application still points to external files, a .dll or .so, so the dependency stays visible. With static linking, the library code gets compiled directly into the executable. The component is in there, but from the outside, you can no longer see it as a separate dependency. It's hidden inside the binary. And it turns out that we're not alone. The C++ community has known this for years. I mean, this post from the C++ community is from late 2024, and it's a good example. Someone here is asking whether managing dependencies will still be the biggest pain point in 2028. And I want to remind you, we're in the AI era. The community knows the problem is structure. The tooling just hasn't caught up. And now, on top of all of this, regulators are demanding SBOM accuracy. Well, good luck. So we understand the problem. Now let's talk about the existing methods for scanning your code and generating an SBOM and why they fall short. Maya?
Thank you. Okay, so let's dive into the existing approach of generating SBOM and why we believe those approaches do not give you the full story. In many cases, they actually can be a bit misleading. This is the common two ways that we have today. Okay, so let's start. The first approach that you can do is before the build. It's called static analysis. The second approach is after the build. It's called binary analysis. Let's start with the first approach. Okay. Static analysis, it's a very common and relatively simple approach. Those tools, they just scan your source code and your manifest based on what they see, and this is the dependency that they are declaring in your project. But as we mentioned earlier, one of the biggest challenges in SBOM accuracy is that declare dependency does not mean ship dependencies. A project may declare many dependencies that never actually make into the final product. Some are environmental specific, we talked about like Windows and Linux, and maybe some are optional dependency. They never actually compile to the final artifact. As a result, static analysis produces a lot of false positive. It creates a lot of noise for customers because it reports every dependency that they can see in the code base. This is the first major illusion in this method. The second problem is actually the opposite one. Some dependencies do not appear in the source code at all. We talked about it. This includes dependency like runtime dependency and maybe environmental dependency and build time dependency. They're only visible during the actual build time. Because those dependencies are not actually listed in your source code or in manifest, static scanners are completely blind to it. They simply miss it. It doesn't exist for them. So with static scanning, you get both sides of the problem. You have too much noise for dependency that were never shipped, but you also blind spot for dependency that were actually involved and we didn't report it. So this is the first common approach of generating SBOM. Let's move to the second approach, the post-build approach with binary analysis, or just like scanning the final executable. These methods do have some advantage because when we look at the final artifact, we avoid the biggest problem that we talked about in static analysis because they don't need to guess which dependency is going to be shipped or not. They actually see the dependency that did ship to the final executable. But now the problem gets much more harder because instead of just reading the source code and declaring the dependency, we have a final executable, it's a binary, and now we are trying to do a kind of reverse engineering and discover the original dependency. Typical, these tools do two things. They do fingerprinting and hashes to compare pieces of the binary against huge, large known database of component. This is like a very difficult problem, and we also have several issues with that. The first one is version and license detection. Even if the scanner can identify a package name, it's often much more harder, sometimes almost impossible, to determine the exact version or license correctly just by hashing from the binary. The differences are just too small. So in many cases, those scanner will declare the package name, but they're not gonna tell you which version it's. And it doesn't mean a lot as a security problem. The second problem is that if, as a developer, I change in this package, even like a small letter, maybe I did some bug fix, maybe I did add some variable, the hash of this package gonna be totally different, and those scanners gonna be completely blind to it and just going to miss it. So this is the second problem. And the third problem is that binary analysis often lose the dependency context. We talked about all those transitive dependency, that we use one dependency and then we get another dependency and another dependency. In those methods, in the binary analysis, they may detect all of those dependency, but they have no way how they came to our code, which makes it much more harder for us to understand, is it a false positive? How do I get there? And if there is a CVE, which other dependency are involved? All those context is lost. And if we're thinking, like Tal mentioned in C++, in static linking that he mentioned, all the data also lost. They completely linked into the final executable, and there is no way for us in those methods to understand the original dependencies. So again, we only have partial picture. So to summarize, we have static analysis. It tells you only what declare and trying to guess the dependency. And binary analysis tell you what it can recognize, but neither one gives you the actually full-time build picture and build truth. In that sense, I'm going to let Tal explain you about our new approach in build time.
Thank you, Maya. Yes, okay. We want to suggest a new approach, which led us to creating our own tool. We call it Build Guard. This approach focuses on creating the SBOM during the build process. If static analysis looks at what you declared and binary analysis looks at what came out, build analysis lets you understand what happens in between. And here why it matters. The compiler is the only process in your entire pipeline that has the complete information. It can compile something it doesn't know about, and it can ignore something that it was told to compile. And it also the last moment before that information is lost. Because once compilation is done, library code gets merged into the binary and labels are gone. Before the build, you have declarations. After the build, you have a black box. When the build runs, the compiler reads every file it actually uses. The linker resolves every library it actually links. And by the way, it doesn't matter how the dependency got there. Vendored into the repo, copied into a third-party folder, downloaded by a CMake script, or fetched with wget. If it got compiled, it's there. And we record everything the compiler touched. That's the difference between declaring and knowing what actually got inside. When we were building this product, we needed to set practices that will allow us to say whether we are more accurate than existing as solutions and be able to actually measure ourselves. What we learned from doing that, we want to walk you through it so you can apply it, our learnings to your SBOM tool. Maya, take it away.
Thanks. So now I want to share with you a few things that we learned while we were developing our SBOM solution. Very early in the process, we understand that if we wanted to build a strong product, we need to have a way to measure it. We need to have a way to evaluate how accurate this SBOM approach really was. And during this process, we found out two very useful approach that I think that you can also use. These are practical ways to evaluate SBOM solution and get a better sense of how accurate they are. So let's start. The first challenge that we faced was very simple. If we want to measure our solution, what do we measure it against? As Tal mentioned before, when we are working on C and CPP, these are not managed ecosystem. There are no one place where all the dependencies are fully and reliably declared. And that creates a real problem. So the first thing that we did, the first approach, is we started with well-known and open source C++ projects, such as OpenCV, Kodi, and Chromium. We went into the GitHub repositories and we look at those projects. We see how they structures. And in many cases, we see that you can actually find a declared third-party directory. You have the README file, you have the CMake list. You have everything you need to help you understand which dependency are in this project. So we thought, okay, this is like a very good place to start. But as we already discussed, just because a dependency is declared in the source code, it doesn't mean it's actually going to be shipped. For example, in this OpenCV project, it's declaring 25 dependencies. So we thought, okay, this is the problem that we're facing. And we took this like one step further. And what we did, we combined our internal knowledge and experience as a company that has been working with build system of 20 years. And of course, we use AI and everything that we can. And we analyzed each dependency and we created a much cleaner list. A list of dependency that we believe that actually going to be built. You can see it in the right. Those processes make we filter out dependencies that were only environmental dependency, flag dependency. You can actually see in the dependency we have like default off or on. We have platform optional obligated. And by doing that, we were able to create several benchmark projects that we had much stronger understanding of the ground truth. And once we had that, we could compare different SBOM tools, including our own, but also every known SBOM tool, and we can test this measurement against those open source projects. This is actually something that you can do. These are open source projects. You can go to the Git, you can inspect the repo, and you can build your own dependency list. It may take you some effort, but all the information is completely there. So this is our first recommendation for evaluation in SBOM. Start with a known open source project. Let's move to the second method. We said to ourselves, okay, benchmarking open source projects is great, but we also need a way to evaluate other kinds of code, maybe internal code, customer code, or just projects where they're not fully listed of declared dependency that we can know. So how we can evaluate the SBOM accuracy there? So the second method that we use is to observe what's actually happening during the build itself. We build this project, the open source one, but also the inner ones and the customers one. And while those projects were being built, we used operation system tracking tool like Procmon for Windows or eBPF for Linux. What these tools do, they record the process list and during the build, and we capture each files that the file system access to it. And the logic here is very simple. If a dependency truly build, then at some point during the build, the system must have access to some files that are related to these dependencies. Now, of course, it's not always a perfect one-to-one mapping. You do need to have some knowledge of build system and some understanding what kind of files you're looking for. But if a dependency was built, linked, or compiled during the build, you should be able to see traces of it. The process list and the file access log, all the data is there. And this gave us a very powerful validation method. Even for a project that we thought we know, we actually found out sometimes that we were misleading or maybe not have the full pictures. So this became our second recommendation. If you want to evaluate your SBOM solution, just trace the actual build process and inspect the file. It's gonna give you much more strong understanding what truly was built in your project. Those both methods are practical technique that you can also adapt, and we encourage you to do it. And now we're gonna move to the demo time.
Oh
Tal?
my, thank you. That's very interesting. We picked up OpenCV as our test project. If you're not familiar with it, OpenCV is one of the most widely used C++ libraries in the world. It powers robotics, automotive systems, medical imaging, computer vision, but it's also a perfect test case because it has very well documented third-party dependencies, which means we can verify our ground truth. We know exactly what should be in a correct SBOM. We're going to run two tools, again, the same OpenCV build. The first one is a popular-based scanner, SIFT, and the other one is our own homegrown tool, BuildGuard, and we're going to scan the same project, the same build. Let's see what each one of them produce. Okay, so here on the left, we can see SIFT. SIFT reported 92 components, but let's look what actually in there. We have JUnit, Gradle, Scala, some GitHub Action CI workflow references, and only one C++ component. But why? Because SIFT scanned every file in the repository. OpenCV has Java bindings, Android support files, CI configuration. It found it all and reported it as software components. Now look at the right side. Every single one of them is real. 0 false positives, 0 duplicates, version and licensing information. We have it for most of them. Let's take a look at FFmpeg case specifically. SIFT reported FFmpeg as a build component, actually 6 times. But let's dive in. On Linux, OpenCV uses whatever FFmpeg the OS has installed. On Windows, it loads the pre-built DLL at runtime, and only if it's present. If it's not, OpenCV falls back to something else entirely. FFmpeg is never compiled into OpenCV. It's optional, platform-specific, and runtime loaded, and also false positive. We did not report it because it wasn't compiled during the build we observed. Build analysis doesn't guess. It only reports what the compiler actually touched. And here is our scorecard. So now, is your SBOM is lying to you? I think you can try and answer that. And we'll open up for questions now.
Cool.
Would love to hear what came up for you, whether it's about benchmark methodology, how build log analysis works, or with specific build system you're running, or what integrating this into an existing CI pipeline looks like. We're happy to go deep as you want. Okay, cool. So let's check out our chat. Why do you want to take the first one?
Yeah, why not? Okay, so I see a question. If my SBOM is slightly wrong, how bad is it in practice? Is this the theoretical risk, or does it matter affected incident response? So the answer is definitely yes. This is actually affect your incident response, because what your incident response is going to do when you have a known vulnerability, or maybe they scare of something, they want to figure out, first of all, are they affected? Is this known CV is in your code? And if your SBOM is not fully accurate, they're not going to be able to do it fast. They're going to need to scan all your source code and file and see all of these files and all the dependency. So if your SBOM is slightly wrong, it just opens you up to more vulnerability and more exposure.
Cool. I'll take the next one. When the recent security incident happened, we scrambled to figure out exposure. How would an in-build SBOM have changed that situation for us? So basically, now you can trace back. You have evidences for everything. The compiler, you can see exactly what files it touched. So you can go back and try to figure out how this CV is actually was integrated to your source code, and from what hierarchy and how to solve it. So it should help you save a lot of time.
Yeah, it's actually a very cool thing that we didn't cover it in the SBOM, but in the build time approach that Tal mentioned, because the way we do it, we have evidence for each dependency from where it came from. So understanding like where it came from is like super easy in this approach.
Cool. I can take the next one as well.
Uh,
What's the operational overhead? Is this something my team has to maintain constantly? So it depends. I mean, we if you choose to use our product, we maintain it for you. But yes, I mean, this is something that you need to be able to run during your CI builds and monitor them lively and make sure that it's reliable and doesn't break, because a wrong SBOM can lead to a waste of time. Wrong CVEs, false positives, and you want to avoid that.
Okay, maybe one more question. This is a good one. Is generating an SBOM during the build gonna slow down my pipeline? What's the performance trade-off? So of course, the honest answer is there is always some trade-off of the performance. But in our build time approach, we do build it in the way that we measure it as a success criteria that it's not gonna be affected a lot in your build time. And if it's gonna be affected, then we wanna improve our product. So our answer for that is definitely you're not supposed to feel your build slowing down just because of you're generating SBOM on it.
Do you want to take another one or?
I think it's a little bit of the time. Yeah.
Okay. So last one. If you're being honest, what's the biggest limitation of today SBOM standards the teams should be aware of? Being honest. Well, usually when you work with SBOMs, you want to verify two things. You want to verify reachability, which you can do with our build time approach, and exploitability. Those two things are the most critical things to most security teams that needs to both generate SBOM for internal use and for external use. So reachability, this is something that is very important. Some teams also try to do to run runtime solutions in production to make sure that it's clear.
Cool.
Cool. So if you want to test this against your own C++ project and see what your current SBOM is actually missing, please reach out. We can do that with you. You can scan the QR code to schedule with us consultation. And if you're working through an SBOM compliance requirements and want to talk through what accurate generation looks like for your specific setup, same thing, just get in touch.
Yeah, you covered it all. Thank you so much for joining us and listen, and we hope it was educational and you did learn some new things, and you're gonna check your SBOM as of today. Thank you so much.
Thank you. Thanks, everyone. Take care.